Hi everyone, this is a presentation related with the research article named Microprocessor Architecture, Scalability, and Error Correction Benchmark. The author for this research is Gabriel Silva Atencio from Latin America University of Science and Technology, ULACIT. The introduction related with the topic that we will have or will be review as part of this presentation is try to talk related with quantum computing leverage, superpositions, entanglement, and interference. Talk about the current era that the noise intermediate scale quantum NISQ device that have right now from 50 to 500 qubits. The key challenge that the transition from, from fault tolerance quantum computing to new models, and the focus related with scalability, error corrections, and architectural benchmarking. What are the research goals or objective for this investigation? First one is they compare the scalability, speed, and error correction across the architectures. Second one, identify the critical threshold for, for fault tolerance quantum computing. The third is develop a unified scalability index, USI, for cross-platform evaluation. And the last one is analyze the pattern trends and the material innovation shaping the field. Related with that, the methodology that we use as part of this research consisting a systematic review of that around more than 150 peer review research article or papers. And the idea that we use the methodology for this review related with Prisma guide. Based on, on this, we run some quantum simulation using Qiskit and Penny Lane for circuit modeling. Also, we have a noise modeling because we use T1 and T2 decay, gate errors, and spatial temporal correlations. And the last one, we have a review of pattern analysis, around 1,243 patents from USPTO and WIPO from 2018 and until 2023, and experimental validation in some equipment related with or simulate hardware related with IBM, IonQ, rigidity processors, and cryogenic testing. This is the key findings when they have the comparison of the architectural. If you see, we have three main categories, that is scalability, USI, fidelity, and limiting factoring. With the architecture, when you are using superconducting, in the case of USI, we have a result related of 0.68 plus less 0.12. The gate fidelity is around 99.3, and the limited factor is crosstalk. In the case of traffic ion, the USI, the number that we have right now is around 0.52, more or less 0.08, and the gate fidelity is around 99-97%, and the limited factor is the gate speed. In the case of the photonic, we have a USI around 0.59 plus more or less of 0.15, with the gate fidelity is around 68% detection, and the limited factor is photonless. One of the important things that we need to arise is that the trade-off between scalability and fidelity is evident on this research. One of the main topics where we identify as part of this research is the error correction cliff. When we try to talk the error correction cliff, the idea is that we identify that the critical threshold around 70, more or less 4 physical qubits per logical qubit. Beyond this point, The idea is that we detect a logical error that exceeds the physical qubit fidelity. The software code requirement shows that more than 1,000 physical qubits per logical qubit, and the implications is high resource overhead for fault tolerance. In the case of the patent trends, we review patents from 2018 until 2023. And one of the key findings that we saw is that we detected around 312 patents grow during this period. That means that the adoption of quantum computing right now in the market in the last 5 years increased 212% in the market. Top players that are moving, impulsing this technology in the market are IBM with control system and Google Cloud that is using right now error corrections. What is the current or the emerging focus right now that we are seeing as part of the market? The cryo CMOS, the photonic interconnects, and the modular design. Also, this indicates that we have a rapid adoption right now for commercialization, but being the technology maturation right now. So the idea is that we need to have more time to try to see how to impulse the massive adoption as part of the commercial trends. The material innovation right now that we're seeing right as part of this the market is the NBT resonator that we have 40.2%, sorry, 40.2% of improvement in coherence times. We have a 2D material that reduces the quasi-particle loss by 2.3 plus. The Josephson junction that mentioned that 57.8 reduction in flux noise, and the implication for the material science is critical for qubit performance. Also, one important topic is what is the current state that we have with quantum advantage. One of the main things that as part of also we're seeing is the short algorithms that we have a 142 increase in the speed up for N15 factorization, the quad mascop that shows that we have 6.2 speed up models gain, and the insight related with the near-term advantage is application specific for quantum. Hybrid quantum classical approach dominate the NIS era. This is very important. The transition from traditional computing to quantum computing needs to have a model that transitions this very well, and this will be the hybrid model that is the combination from traditional computing to quantum computing. Okay. This is the model related with the Unified Scalability Index, USI. This is a metric that combines qubit quality, architectural scalability, and error correction efficiency. As you see, this is the formula that we are proposing as part of this research, that this formula is validated via Monte Carlo simulation and correlates with algorithm performance related with R 0.79 for BQE. Okay, this is the recommendation that we propose for future work. One of the things is the co-design, align algorithm development with hardware constraint, material discovery, high throughput screening, and machine learning models, modular architecture, photonic interconnects, distribute quantum computing, and also standardized metrics, application-specific benchmark beyond qubit count. Okay. And the conclusion for this research is very important that no single architecture meet all the fault tolerance requirements. Superconducting leads in scalability, trapped ion leads in fidelity, error correction overhead remains major bottleneck. Interdisciplinary collaborations is essential for scalable quantum computing, and in the future, application-specific quantum processors, not universal machines. This is my presentation related with this article research This is the knowledge and my content in case that maybe you have a or wants to have additional information and open to share that. Thank you.